demonstrate this editor. This editor, we're gonna build these, illustrate these arrangement of logic labeled finite state machines. We're gonna show how to build this. They are based on this meta model. So it's based on the Eclipse modeling framework, but it's all written in Java, so you can run it by just downloading it. So let's demonstrate that. So I'm going to download the editor. It comes down here, and in my terminals here, I'm gonna, in this demo, I already have two folders. So I'm gonna go to the MiEdit folder, and I'm gonna move from downloads the MiEdit tar. It's usually, you may have to unzip it, but my download already did that. So I'm gonna move it here, and then I'm gonna extract it. And sorry, the wrong argument to extract. There we go. And now we just can run it because the tar file is in the distribute folder as MiEdit. So you run this, and a screen like this of the editor will show up. And as again, we're gonna build this machine. So I'm gonna start by building the first machine, which is called starter, which has a state called initial. So let's keep this one in mind here. And so I'm gonna say file, new, and choose a folder. And at the moment, the arrangement, I'm gonna call it demo Fisher Boolean. That's gonna be the name of the arrangement. And the very first state machine is gonna be, as I mentioned, called starter. And it only has one copy, and the first state is called initial. And we can already add the first type of statement by clicking on the onEntry section, and we're going to add a statement of type output line, which has initialize the global variable. Okay, now here we don't put quotes. And once we do this, we have our first statement. The next statement is an assignment where we need these global variables. So we say variables, we add a global variable. The variable is called shared x. And it's an integer, it's shared, so it's in the whiteboard. And its maximum value happens to be 2. We're reproducing this diagram where that variable maximum is 2. So we enter the maximum value, and we need a defined constant called not a thread. So constants add not a thread. Okay, and that one we're going to choose the value 0, which is the default. So we are click here, and I'm going to add a statement, but now an assignment that has an integer variable in the left hand side. So it's a whiteboard variable, which is an integer. We only have one, so not much to choose. And the right hand side is a predefined integer constant, which is the only one we have defined so far. So we have completed this machine. So to show you that, I'm gonna now download the transformer. So I'm gonna download this guy. It's coming down here, and I'm gonna use the second screen here into my already existing folder called transformer, and I'm gonna move from downloads this Java tar here, and similar as before, extract the transformer, and the transformer is a Java program, so minus jar, and it comes as part of the distribution. And this is a transformer. If you don't say anything, you get some of the, so we need to say an output and an input. So I'm gonna copy from where I had the, I think I call it demo Fisher Boolean or XMI file. I'm gonna copy it here. And now when I do this, I'm gonna say the output option is dot, and the input file is the demo file we're building today. All right, so now you can expect, now as a result of that, we have a dot file. Let's have a look at it. And that file at the top has some instructions on how to construct a PDF. So I'm gonna use those instructions. And so now I have a PDF file, and I'm just gonna open it and bring it over to you here. And as you can see, what we have constructed with the editor is precisely this little part: one machine, one integer word variable, one constant, and one state with one assignment. So now we're gonna close this and add the second machine. I'm gonna construct these first thread machine. So we go back to the editor and we say machine add, and the name of this machine in the diagram here is thread 1, so that's what I'm gonna call it. So thread 1. Okay, so now in this case, one copy of it. It's in first state is called T1 non-critical section. So I'm gonna change the name of the initial state. Okay, and also notice that it has a local variable. I'm a thread. So now what are we gonna do? This is the machine we're editing, so we're gonna say variables add, and the variable here is called I am thread. Is it what it's called? Let me just double check. I am thread T1. It's a bit more specific. I am thread T1. It's a variable, but now we have to say it's integer as well as before, but now we have to say it's local to this machine that we're currently editing. Okay, and its max value happens to be 2, so we're gonna copy that too as well. All right, we have that variable, and this machine uses sensor variables called how much delay it is out of the non-critical section. So we're gonna need to add some variables that are, this is the first name of one, but they are Boolean, but they are sensor variables. Okay, so that's the first one, and there's another one for the delay out of the critical section here. So we're gonna go to variables, add. Here's the name of that variable. It happens to be Boolean and sensor. So we're ready to maybe write this little bit here. So I'm gonna move it there and keep my editor. All right. So let's add a state. The next state is called T1 wait. I think I call it T1 wait. Okay. There's another state called, so I'm gonna add all the states. State add T1 assign. Okay. T1 critical. I'm adding them in the order of their numbers here. So state add, and this one is this one here, T1 critical section, and the last one is T1 let go. State add T1 let go. And now with this button, I'm going to choose, here are the states that I have added. By default, the initial state. Okay, and we're going to add the first, you know what to do here now. We want to add a statement that has an output line, and we write the string that belongs here. So that string, we just put it here. All right, and we also have an assignment now. So remember, we go here, add statement, but it's an integer on the left-hand side, but now not a sensor, but a local to the machine. and there's only one variable of that kind that we have declared. The right side is an integer constant, and the integer constant here is not 0 but is 1. Okay, so we have wait doesn't have anything. Assign has some behavior there, so we're going to go to the state assign, and in the state assign we have assignment again. So we go here, we add a statement that is an assignment. The left hand side is a whiteboard variable. We only have shared x that is integer. All right, and the right hand side is an integer variable reference, which is a local to this machine, and there's only thread 1. So that's the content of the behavior for the onEntry of assign. We go to critical section, so let's go to states, choose critical section. In that state, we're gonna add a statement that is an output line. The string that goes there is this string, so I'm just gonna paste it here. Okay, that's the whole of. Now we're gonna go to let go. All right, so we're going to go to states. Let's edit the state let go. The state let go has an assignment as well, so we add a statement which assigns to an integer variable in the left hand side. That integer variable is the whiteboard variable shared x, and on the right we have a predefined integer constant, and the only one that we have is not a thread. So we have all the states. So now we're going to do the transitions. So we need to add a transition. So we need to say which is our source. We have to make our you have to be in the source state, in this case in the non-critical section as your current state, to add a transition, and the target is wait. So we go wait. Okay, and we can, there's many options here. We actually gonna do a Boolean variable reference, and remember we have sensor variables, and out of the two sensor variables we choose the one that's non-critical. Okay, to show you that we've done some progress, I'm gonna repeat what happened here before. So I'm gonna copy what we've done so far here. So I'm moving the XMA file. Then I apply my translator. Remember, that's the Java file. Now I do the dot program. And now I open the PDF that we've done so far. And look at the PDF we built so far. So that was the first machine. The second machine, we have all the states with their behaviors inside, and we have added one transitions here. So what remains now is to add the remaining transitions. Remaining transitions, so I'm gonna close this, and we only done one. So we go back to our editor, and let's make wait is the source of the next transition. So let's go to the state wait, that's the source, and we're gonna add a transition to assign. So transition add, the target state is assign, and here we don't have a Boolean reference, but we have a equals expression, so that's towards the bottom here. And now we're gonna select an arithmetic expression for the left side. That's not a thread, so that is a integer variable reference. No, it's not an integer variable reference. Not a thread is a predefined constant. All right, remember, not a thread is a predefined constant. And there we have the only one that we do. And we select the one on the right side. That is the variable. So we need a integer variable reference to a whiteboard variable that is an integer that's shared x. All right, so we've done this transition. That's all that comes out of wait. So we need to go to assign, which has two transitions going out. Transitions, and in what order? This one 1.3 goes before 1.4. So we're gonna add this one here first. So as I said, the first thing is to change the state to assign as the source state. So that's our current state that we're working on. We add a transition whose target is wait. So let's go to wait. Okay. And the transition is a not expression. Okay. And now we're gonna put what is negated in. So what is negated is, now you've seen how to do an equal expression. So we need the left side, which is the local variable, so integer variable reference to a local in the machine, and amthread T1, that's it. All right, and now the right side is the variable, so integer variable reference, but now it's a whiteboard variable, is shared X. Okay, so we've done this one. This one has two transitions going out, so now we need also to add the second transition out of assign to critical section. So the state is called critical section, and we need a Boolean constant, and we choose true, and we done this one. Now we need a transition from the critical section to let go. So the current state has to change to the critical section. That's our source. Our target is let go. So transition add, the target state is let go. And what we have here is a Boolean variable reference. It's a sensor. It is a whiteboard variable, but it's the other one, in how long we are in the critical section here, the delay. So we say, okay, we've done this transition. Now the last one is from let's go back to, so let's make the state the let go. That's going to be the source state. So now we have a transition add. Our target state is our initial state, which comes here by default. So say okay. Variable reference, no, we want a Boolean constant, and what comes here is true already. So okay, I believe we've done all the transitions. So I'm going to use the transformer again. So I copy the produce file from the editor, I translate it, I apply dot, and then I open it, and here it comes, and we have our full first thread here. All right, so I'll leave you as an exercise to produce the other one, but it's exactly a copy of this one, just slightly different names. What I want to show you now to end this video is that the transformer can produce nuXmv input. All right, so we do that. And now, if you look at it, we have the corresponding model for model checking. So you can inspect it if you want to do that with an editor. And you have here the components. All right. And let's quit it. And I can run nuXmv minus ETT demo Fisher Boolean and do some trivial checking of the model that no deadlock exists. All right, so this is a quick overview of how the editor produces output that can be visualized with dot, or we can apply a model checker to the nuXmv transformation.